Hi, everyone. Welcome to the last track of Spark Summit Europe. For the next talk, we'll have Julian Dragos and Luc Boulier from TypeSafe to talk about Spark streaming in production on Mesos. Please help me welcome Luc and Dragos. Julian, sorry.
Thank you. Can you hear me? Seems to work. All right. Good afternoon, everyone. My name is Julian Dragos, and I'm working at TypeSafe. I'm a tech lead, and I'm working on the Spark team with TypeSafe. And with me, I have my colleague, Luc.
I'm Luc Boulier. I'm also working at TypeSafe in the Spark team.
So today, we're going to talk about running Spark streaming jobs on Mesos. And it's fairly easy to run a Spark streaming job on Mesos, but running it reliably and to ensure zero data loss, maybe it's not that obvious. So we're going to walk you through a couple of points that you should be aware of if you want to deploy Spark streaming jobs that run and don't lose data. So here's the rough agenda. How many of you have used Mesos, Spark with Mesos already? OK, just a couple of hands. So then it's good that we have maybe 2-3 slides about Mesos and how Spark runs on Mesos in general. And we're going to talk a bit about different deployment strategies of Spark than when it runs on Mesos. Let's say the biggest part of my part of the talk is going to be fault tolerance with zero data loss. So we're going to look at several failure scenarios and see how you can guard yourself against those type of failures. And to close, Luc will talk a little bit more about streaming back pressure. So if you've been in this room at 3 o'clock, there was a very nice talk by François Garillot and Gérard Mas, where they actually demoed Spark streaming with back pressure. We're going to talk a little bit more about, Luc is going to talk a bit more about how that's actually implemented. All right. So Mesos. Mesos is a distributed operating system for your data center, if you will. It's a generic cluster manager that can run any type of load, not just big data loads. Like Yarn is specialized for big data. Mesos can run Play applications, even Cassandra or HDFS or anything. It's fairly proven technology. So Mesos is not as young as it may sound. It's in production at companies like Apple and Twitter, so deployed on very large clusters. And last point, we really like at TypeSafe, we really like Mesos, and we really like Spark. So together with Mesosphere, the company behind Mesos, we decided to contribute and make sure the Spark framework implementation, or the Spark on Mesos parts, are running very well. So we've been putting effort into that, and that's why we talk about it today. So I mentioned earlier that Mesos is a generic cluster manager, so it can run many different loads. Here's a couple of existing frameworks. Framework is the terminology of Mesos for any application that runs on a Mesos cluster. So you can run HDFS or Marathon, Cassandra, Elasticsearch, even Yarn. There's a project called Myriad that achieves that, and of course, Spark. So how does a Mesos achieve this kind of generality? It uses a trick called two-level scheduling. So Mesos is managing a cluster of machines, and as these machines become available, because a previous framework just finished, it offers those resources to frameworks. And the resource can be CPU cores, memory, even disk or ports. Now, a framework implementation, so in our case Spark, can accept or reject such an offer. Once it accepts an offer, it can schedule, as it likes, tasks that run on those resources. So I bet you've seen this picture many, many times so far. So this sort of schematically depicts how Spark integrates with any cluster manager. It's generic. So on the left side, you have the driver, and the rest of the picture depicts the cluster, the manager, and different nodes, or in Mesos terminology, slaves, that run Spark workloads. So there are basically two axes where you can choose something when you deploy on Mesos. The first one is, where do you run your driver? So remember, the driver is the main of your Spark application. It can run on the client, so the computer on which you're typing. It can be a laptop or whatever, your desktop machine, or inside the cluster. And the other question you have to answer before you actually launch something on Mesos is whether you want fine-grained or coarse-grained mode. And I'm going to talk about that just in a second. So the driver placement. This choice is fairly easy. So in client mode, it's very easy, but if the machine stops, so if you pack your laptop and go home, the job is lost. So you can do this for quick and dirty trials. You want to experiment with something, you have some exploratory analysis you want to type quickly, you can use client mode. The cluster mode has the advantage that the driver is managed by the framework. So you can go home and it can keep running. It's slightly less convenient, though, because once the driver is inside the cluster, the Spark UI may be hard to find. The Spark driver may be launched on any machine in the cluster, so in order to find it, you need to know what machine to connect to on port 4040 or whatever. Spark Shell, which is a very convenient tool, also depends on having standard in and out and error available, while if this process is launched inside the driver, it's harder to get to those streams, of course. So maybe something like Spark Notebook is then a better UI to connect to your jobs. OK, the executor policy. So fine-grained is a mode in which every Spark task, if you've seen earlier Andrew's talk about visualizing your Spark cluster and how tasks are deployed, a Spark task is it's the unit of parallelism in Spark. So every Spark task can become a Mesos task. Resources are acquired and freed during the lifetime of your Spark application, so it leads to very good resource sharing. Other frameworks that also run on Mesos can use those resources while a Spark app is running. It does have a slower startup time because every time you acquire a new resource, you have to provision, let's say, that node. But it's a good match for relatively static streaming and batch jobs. The coarse-grained mode is slightly different. When the Spark job starts up, first it acquires the Mesos executor, the Mesos resources that it needs, and then it holds on to those until the Spark job is finished. So there is no one-to-one correspondence between Spark tasks and Mesos tasks. This leads to pretty good latency if you're doing interactive sessions. So the resources are always there and available, but they're also locked for the duration of your Spark job. So other frameworks cannot use those resources. And if you think about Spark Shell and you just forgot to exit from the Spark Shell, other users on the Mesos cluster will be locked out of the resources that Spark Shell is actually not using, just acquired. OK, so let's move on now to Spark streaming. And I'm not going to talk too much about streaming itself. I believe everyone knows already that Spark streaming is really using mini batches, and data comes in, it is divided into batches, and then the Spark core execution engine is what actually works on those batches. So let's have a look at this diagram, and you will notice that two executors are slightly different. So in a Spark streaming application, in some executors, we can have the so-called receiver, which is a component that ingests the data that comes from outside of Spark. These are long-running tasks, if you will, at the implementation level. So they are deployed on executors. In this picture, you see also a number of square blocks. Those are just that's the data in memory that is received through the receiver. And that is replicated inside the cluster. So those blocks are actually probably on other nodes as well as data comes in. So for the moment, we don't care where the driver is. It can be inside the cluster on a client machine. It doesn't really matter. All right, so let's see what's the simplest failure scenario. And that is probably an executor dies. Now, this is not something extremely special. Spark Core has been dealing with this type of failures forever. So what happens here is that the executor goes down. Spark Core will, any data that is already inside an RDD and is being processed is not lost. It will just recalculate that part of the RDD that got lost, and it will sort of bring it up on another executor. What is different, though, is that we do have a receiver, and we do have some data that may not have been replicated yet. So we might have data that was received, and it lives only on this particular executor that just failed. So how can we make sure we don't lose data in such a case? So the solution here is to do what databases do and add a journal or a log, the write-ahead log, which usually sits on a reliable file system. So in this example, I said it's HDFS. So now, in this mode of execution, when the wall is enabled, receivers first save data on this reliable storage, and only afterwards they start executing, creating RDDs and executing the Spark jobs. This obviously slows down a little bit the rate at which you can ingest data, but the benefit is that your data will not be lost in the event of executor failure. The driver also saves some metadata in this checkpoint directory. Actually, the actual implementation is based on a checkpoint directory where all this data is saved. So now if, OK, I got a bit ahead of myself. This seems to be fine, but if we think a little bit more, we realize there's still a failure mode where data can be lost. What if the executor dies after data is received, but before it's reliably saved in the wall? So to handle, well, we did diminish a little bit the window in which failure can occur, but we still need an answer. And the answer here is to use reliable receivers and data sources. So that means we need the cooperation of the data source. We need to be able to send an acknowledgement signal back to the data source saying, the data that I have received up to now is safely stored, so you can advance. And if such an acknowledgement signal is not received by the data source is able to replay that data. So of course, Kafka is such an example, but there's also Flume and Kinesis. So there are a couple of data sources that can provide this ability. And this is needed to achieve zero data loss. All right, so we're not done yet, because the driver itself can also fail. So if the driver dies, what can we do? Well, the first thing we need to do is to restart it, because a Spark streaming job, it's supposed to run on forever, let's say, so nonstop. So assuming we can restart the driver is able, using the wall, to read the metadata that was saved there, and the data can be later used to process, well, to run the transformations and, well, the actual Spark job on data that has been reliably saved there but not yet processed, and continue execution with whatever data keeps coming through the receivers. So the only question now remains, how can we make sure the driver is automatically restarted and we don't have to watch over it ourselves? And driver restarts are a feature of the cluster mode deployment. So if you remember the two modes, client and cluster mode, of deploying on Mesos, cluster mode can do that if you pass a command line option called supervise, and it automatically restarts a driver if it realizes it crashed. There's one little thing you also need to do inside your Spark streaming program. You have to not create a new streaming context every time. You should actually use get or create, pointing to a checkpoint directory. And in case the job is restarted, because of a failure, of course, it can actually read all this metadata from the checkpoint directory and respawn the whole job and continue where it's left. However, if you run on Mesos, there's an additional option or an alternative called Marathon. How many of you have heard of Marathon? Everybody, much more than people who are using Spark and Mesos together. So Marathon is a framework, so it's a distributed application running on Mesos. It's a framework that makes sure long-running processes are always running. Think about init scripts on a Linux box. And Marathon is fairly easy to configure, and Marathon can watch over your driver and restart it if it fails. So you don't really need to do cluster mode deployment. You can use Marathon and be done with it. So what we believe is a good setup is to deploy, of course, the driver inside the cluster, so you're free to turn off your laptop. And Marathon is, in my opinion, more flexible right now than cluster mode deployments. I would go for that. Enable the write-ahead log if you're using a reliable source. For Kafka, there's an alternative. There's the direct Kafka driver, which doesn't use receivers, and it can achieve the same zero data loss guarantees without going through the wall as well. And enable back pressure. So here's where I'm going to hand over to my colleague Luke to talk about what back pressure is.
Thank you, Yan. So back pressure in Spark streaming. So Yan described how to set up a resilient system, such a way that your Spark job never dies and process the data and keep the data which is coming in. But it still doesn't mean that you will have a stable system. One of the next problem will be if the data is arriving too fast in your Spark job, in your Spark streaming job. You have a schedule, you have a batch interval in a Spark streaming system, and if it takes more time to process the data in your mini batch than the batch interval, then you start to get a scheduling delay. The processing of the next batch need to wait for the previous batch to be finished to continue. And as it goes forward, you start to accumulate really good big scheduling delay. At some point, if you in addition to accumulating scheduling delay, you also keep all the data which is to be processed in memory. You can, if you set up your system to cache the data in disk, then it will start to spill to disk. But your system is already too slow to process the data normally, and you just added an I/O operation on your whole system, so it will get even slower and not process enough enough to get all the data in. And in the worst case, if you didn't set up for caching on disk, then your memory can just be full, and the driver stops, and well, you're basically dead in water at this point. Up to Spark 1.4, there was one property was possible to set, which was the max rate on receivers, which set to Spark to limit the amount of input to a specific amount of record per second. It is very difficult to set at the right limit. You have to be conservative. Because you really, I mean, if you want your system to work 24/7 all the time and never crash, you need to make sure that you never go over the limit, the real limit of your system. So you have to set a limit which is low enough. Another problem is it is not it's not flexible. You set the same limit for all the stream inside your Spark streaming job. The solution for this kind of problem is back pressure, which is also called flow control. The basic idea of back pressure is that if you have a slow consumer, it should be able to tell the producer to send less data. A basic example is really TCP. If you look at the protocol level of TCP, every time there is data, well, not all the time, but a lot of the time going back between the client and server, there's information from the receiving point saying that this is how much data I can receive in the next frames. If the receiving part of the TCP connection says I cannot receive any data anymore, the producer doesn't send data anymore, and on your application you get an error saying that I cannot write in the TCP channel anymore. In Spark 1.5, us at TypeSafe, with the help of the Databricks, we added a dynamic rate limit computation, which is based on 3 parts. The first part is a rate estimator. So at the end of each processing of mini batch, there is a computation to estimate the number of record of elements that can be safely processed during the batch interval. Then this information is sent to the receivers, and on the receiver, especially for the TCP-based receivers, there is a rate limiter which blocks the incoming data if it's going too fast. This information is also sent to the Kafka receiver, and is directly managed by the Kafka receiver and sent to Kafka to say this is exactly how much data I can receive, and don't send more than that. The rate estimator, it's using the information which is available at the end of the completion of the processing of a batch. So processing delay is the time it took to process. The time it took to process the data. Scheduling delay is the delay, the time between the time the job wanted the streaming application wanted the job to start, and the time when the job started effectively. So one of the worst way to find out what is the maximum limit for your streaming job is to just take the number of elements and divide by the processing delay. That gives you a rate in second of how many elements you're supposed to be able to receive and be safe and not have any problem. But that doesn't take in account any accumulated delay. So if at some point your job is too long, you start to accumulate delay, and if you always stay at the maximum, the delay will stay. So the actual solution that was done in Spark 1.5 is to use a proportional integrated derivative estimator, so PID for short. So this is really not new technology. It's something that started to be used, for example, in autopilot for used sea ships. When you need to turn big cargo ships, you can turn the wheel of the ship as far as you go. It will take a long time before it starts to turn, and you need to stop to turn the boat early enough so it doesn't turn too much. So it is a system to compute exactly how much, in case of the ship, what the angle you need to exactly give to go to the right direction. So this is a graph of a few tests I made to prove that it was a good idea. So the graph in the bottom is just what the data which is sent. So we just send a spike of data. It's just double the number of elements we can send. The first graph is using Spark without any rate limiting, not even the static rate limiting system. And the second part is using the dynamic rate limiter. So what you can see, so each bar is the time it took between the time the job was supposed to start and the result was produced. And so you see that with the system without dynamic rate limiters, the scheduling delay grow very fast. And in this example, basically in 2 minutes time, there is only already a 45-second delay. So it can grow really, really fast. And just by the original the extra time it takes to compute the batch is not way bigger than the batch interval. And on the second graph, so we see also a bit of scheduling delay because the computation is dynamic, so you need to react to the fact that there is a change of the schedule of the time it takes to process data. So yeah, so there's a bit of scheduling delay, but it is absorbed, and then after that it is stable. Yeah, and something which is not quite visible a lot, but you see the little seesaw kind of line. It's the memory usage, and it's going down fairly slowly, but it's going down. This test run only for 2 minutes. If I get the same test running for 30 minutes with a spike of 30 minutes, the system will just die. Yeah, so just a summary of back pressure in 1.5. Each input has its own estimator, so if you have a fast input and slow input, they get the right data. It works with all stream receivers, including the Kafka receiver, and it's enabled just using two properties, just to enable back pressure and to put a low limit of how low you want to get your data. So a few limitations. It's using a linear assumption. So if it assumes that it assumes that in general all the records take the same time to process. So if you have a job which is take longer in non-linear fashion, it might not be good enough. Yeah, and so if you use a normal TCP receiver, the normal text receiver, the back pressure is then given to the TCP channels. And so on the Spark side, we compute a really nice value of how many records we can process in the batch interval. But this information is lost through TCP. We just the data is just blocked when it is received at the Spark receiver level, and the producer of the data, so the server sending the data, has no real information of what is a good amount of data to send to the receiver. So that leads us to the next point, which is doing back pressure with reactive streams. So reactive streams is a specification for interfaces between systems that does back pressure. So you can find the specification on reactivestream.org. It's really, really simple specification. There's 3 interfaces and 7 methods total. So it's really simple to implement. And the goal so Reactive Streams is really just interfaces. The goal is really to be able to take a system which support back pressures and link them together. And so the idea to add the reactive stream to Spark streaming is to have a better control of the back pressure. So instead of losing the back pressure when we get to this TCP, the back pressure is sent to some code which understood a reactive stream and understood back pressure, and it is sent all the way to some part of the production chain of the data. And in the production of the data, if it starts to notice that the amount of data is too big for whatever is downstream, it can make an intelligent choice of what to do with extra data. So basic example could be like if you're processing logs, and then you get a huge spike of data, which might be because you basically have a problem in your web applications, which means you have a lot of errors. And all the warnings that you were maybe processing before, you don't really care anymore at this point, because what you care is the errors. So you can, at this point, if you see that your streaming job is not fast enough and you have some warnings and some errors, at this point you can decide, OK, I don't care about warnings anymore, I just throw them away. Or if you're processing real data, well, logs is real data, but I mean more important data, what you can do is maybe some sampling. And at this point, you start to sample your data, and you know how much what the amount of data you sample. So you can also send downstream information saying that, OK, this is the data you need to use to compute some machine learning algorithm. And in fact, it's only 80% of the data. So when you start to compute error rates, you need to know that you don't get all the information, you got only 80% of the data. So a little graph kind of trying to show the interesting part of using reactive stream instead of the normal TCP pushback. So on the first, so the graphs are basically the same as before. It's just so the top one is using the normal TCP connectors, and the bottom one is using a reactive stream connector. So and on the second part of each chart, the red bars are when the producer noticed that it cannot send all the data he wants. So in the TCP case, so you get the spike, and you get a long time almost up to the end of the spike for the producer to notice that, oh, something is wrong. And at this point, it basically doesn't have much choice to just, drop all the. In my case, I just drop all the data. It was simpler. It's just it's test cases. And on the reactive stream, you see almost, it takes a really short time, but really fast, you notice that the producer notices that, oh, there's too much data. So at this point, we start to drop data. And I mean, in my case, I drop data, but we can do something smarter. Another thing to notice with something I really don't like with using TCP to do pushback is you have the spike, which ends right there, and basically the time when you need to drop data also end about the same time. So the system, as soon as the spike is done, the system gets back to a good state. On the case with the TCP, you see that you have still a fair amount of time where you have long execution and drop of data. The reason for that is TCP has a really huge, can have a really huge cache, which you don't really control at all. It's the whole chain from your producer to the receiver of TCP, which cache data. And you have no control. So your spike might be done, but your system still have to process some data which is old. And so Reactive Stream is not yet in Spark. I'm not sure exactly if we can get it in 1.6. So we need to do a bit of work. We have a proposal to be able to get. We just need an extra bit of data to be able to get everything we want. So we are working with Databricks to get this extra piece of data, and we expect to have it in 1.6. And that's our presentation. If you have any question, we have 1 minute. Any questions? all the way bottom.
Yeah, sure.
Thanks for the run. Quick question to you. So in terms of monitoring the streaming jobs, obviously the scheduling delay is one of the quick ways to figure out that back pressure is building. Would you recommend any other metric when you have this back pressure solution really in place to notice that there is some delay in processing the data because your job is not keeping up with the...
Well, the first information we get is not scheduling delay. The information we use is not scheduling delay. It's just how long it takes to just process the batch. If it takes more than the batch interval, then we know there is a problem. And then the PID computation starts to reduce the maximum rate. And then the PID also has information, the scheduling delay, which happened for each job. Mm-hmm. And if needed, it reduces even more the maximum amount of data it says it can receive to be able to shrink the scheduling delay.
Okay, so essentially my way to understand that there's back pressure in the system is to look at processing time, which is close to the maximum batch time? Okay,
yeah.
Cool. Thanks.
Thank you, Luke and Julian again.
Thank you.
Thank you.